Welcome to our next lesson on magnetic fields and forces, and today we're going to look at how a moving charge interacts with a magnetic field. And before we do that, I just am slowly realizing how very difficult it can be to describe 3D interactions, and so I want to be a little more clear from the last video, and so I found some better representations of what we were looking at last time. And so here is the right hand rule again at work. Right hand, left hand rule. Right hand, because we're looking at current here, and current is by default positive, so right hand is used. And it's very importantly that the thumb here represents the direction of the current, and the fingers, the way that they coil or loop around, is the direction that the magnetic field will be generated in. And it's important to note that this works for circuits, and you may think, well, but circuits aren't moving positive charge, they're moving negative charge. And so how does this work? And so what I think is also important to note is that there's a lot of symmetry here. And so here's the right hand rule at work. Positive charge, right hand, moving upwards, and so my fingers coil like so. Electrons aren't positive, and so if current is represented by positive charge moving upwards, actual electricity is negative charge moving downwards. And so you'll see that the coil, the way the fingers wrap around the whiteboard markers in this case, is the exact same directionality. So this representation that we saw still works. And the other important aspect is, what does this represent? Well, this is charge, electricity moving. And when we have charge that's moving, it will generate a magnetic field. If the charge is moving straight, it generates a rotating magnetic field. The other alternative that we looked at is, well, what if the charge is moving in a rotated fashion? What if the charge itself is doing the loops? Well, then the magnetic field that gets created is straight up and down, or very similar to that of a bar magnet. And that's what we were trying to look at last day. It's just so very often that you find the right images right after you needed them. For today, however, put that back up there, and for today, however, we are going to look at not what magnetic field is produced by a moving charge, but how does a moving charge interact with an external magnetic field? So we'll get right down to that. And to do so, we've got a little bit here already written, stating that any charge, positive or negative, that moves through a magnetic field, which we'll call, as we always do, B. B is our external magnetic field. Any charge that moves through an external magnetic field will deflect. In other words, it will experience a force. It will experience what we call a magnetic deflecting force. And mathematically, we can calculate the magnitude of the force. The direction of the force is dictated by the left-hand, right-hand rule. And so the direction of all of these is important in the end result, direction of the force is dictated by kind of like the second iteration of the left-hand, right-hand rule. Similar to what we just looked at, but just slightly different. So let's actually take a look mathematically. The magnetic force that gets experienced is Q multiplied by perpendicular velocity. We'll talk a little bit about that more. Q multiplied by the perpendicular velocity multiplied by the magnitude of the magnetic field. Okay, remember that that's your absolute value signs, meaning the magnitude. Okay. These are the three key players in figuring out how much force there is. In terms of direction, however, well, let's just set up a situation. Let's say we have a magnetic field. We have a north pole, we have a south pole. So we have two bar magnets, and so the magnetic field points this way. Here is the direction of the magnetic field. And let's say we also have an electron that's moving perpendicular. That will represent the direction of the velocity. And what's very key is that, well, the direction of the velocity is perpendicular. If the velocity were to come in at an angle, well, we simply have a side equation here that is the perpendicular component of that velocity. The key idea being that if the magnetic field and the direction of the electron are parallel, if they're the same direction, we actually don't get a force here. So if the electron were moving in the same direction in between these magnetic poles, it would not experience a force. And it has to be a perpendicular component or exactly perpendicular. So let's get into our left-hand, right-hand rule. We have an electron moving here, so that's negative charge. That's left-hand rule. And our left-hand rule has three things we have to keep in mind. So we have index finger. This will represent direction of the magnetic field. And these are all the same for the right-hand rule as well. It's just we're doing left-hand because that's negative. So even in the right-hand rule, the index finger is still the direction of the magnetic field. The thumb is the direction of the electron, or the direction of the velocity initially. And finally, the middle finger is the direction of the magnetic deflecting force. So we'll just say direction of the force that the electron will experience. So here's a little bit about how that works. And sometimes when we're doing this two-dimensionally, hopefully it'll make sense, but let's actually get the direction that the electron will deflect. So the thumb represents the direction the electron moves initially. So electron's going that way, using my left hand. The magnetic field is my index finger, and that points this way. So then the next step is just kind of put your hands into like this configuration, I guess, and make sure they're all at 90 degrees to each other, I guess. 90. That's kind of what we're doing. And so we'll line it back up again. The deflecting force here is kind of downwards in a way. It looks like it's going into the page. And so actually that's what we say is the force here, the direction of the force, is into the page. Deflecting force is into the page. And, well, into the page we actually have a special kind of way of signifying that. If this is that way, and the electron's going in this direction, into the page looks like this. We actually draw an X. So that dictates that the force will go into the page. Conversely, let's play a little gymnastics here. Let's reverse the direction of the electron. So let's say instead of going in its original direction, we reverse the direction of the electron. This is kind of not doing it to just represent. Sometimes you have to go back and check, well, which one is, okay, reverse the direction of the thumb. Okay, so opposite to what it was. So if the electron were moving instead of in this direction, but was going this way, it would deflect upwards. Instead of into the page, it would come out of the page. And so this is our deflection here. And let's say if we were an electron going this way, the force would be out of the page. And the symbol that we use for that is a dot. There's one kind of easy way to remember this in general. Think of an arrow, like from a bow and arrow, and you have all of the kind of fletching feathers on the end. You have the point at this end. So if the arrow is flying away from you, you see the feathers, and if the arrow's coming towards you, you see the tip of the arrow, the point of the arrow. So that's kind of how I remember. It's just an arrow into the page or away from you and out of the page towards you. Okay, so we can do another example. I think that would be helpful. So let's say we have a magnetic field that magnetic field points into the page. And I'd say you'd see this written kind of a couple different ways. Magnetic field points into the page or away from you. So how we interpret that would be our magnetic field looks like this. Points away from us. And let's say an electron, actually let's say let's say a alpha particle travels this way into the magnetic field. Well, we'll be sure to remember that an alpha particle has a positive 2 charge, and the magnetic field points this way. So the thing we want to know is what's the direction of the force. So, okay, positive charge, so we're using our right hand. The magnetic field points downwards into the page or away from you. So we'll do this kind of 2 ways. Magnetic force points downwards. The alpha particle is moving that way. That's hard to see. So therefore the deflecting force is that way. So upwards. Okay, so let's do a similar thing where, let's say instead, an electron moves this way through the same magnetic field. Electron is negatively charged, so then we'd have this. Direction of the electron, direction of the magnetic field. Now the force is downwards. So this direction of the force will be downwards. Okay. I think I might have to. Yeah, we should. Alright, so try this another way. Hello. And so the first example was alpha particle. So the magnetic field points away from you. Okay, so here's my right hand. It's pointing away from me. Then, or actually, let's do the electron first. Electron first. So left hand, magnetic field points away from me, and the electron was moving to the right, and so the magnetic deflecting force is downwards. Does that kind of make sense? Okay. So next up is the right hand. The magnetic field points towards you, and the direction is of the alpha particle is not towards the left, but towards the right, and so the magnetic field is upwards, and so that's kind of how that works. 1, 2, 3. Hopefully that makes sense. Next up, we have almost the kind of same equation as before. We have magnetic deflecting force again. Instead of just doing individual charges, the magnitude of the force for a wire, or the electricity flowing through a wire, is equal to the current flowing through the wire multiplied by the length of the wire, so that's L, cursive L, by the way. So the length of the wire, and then multiplied by the magnitude of the magnetic field. So that would be how much force a wire would experience if placed into a magnetic field. Depending on strength of the magnetic field, how much current you force through the wire, and the length of the wire itself. So, for example, we could have, this is where the kind of circuits comes into play. We have a battery, and we could run a current through, and we could have a bar magnet sitting on either side of the wire. Let's actually just make it a little more symmetrical so it looks nicer. Change all that much. So here we go. Now, even though the magnitude of the force represents the current, we still want to remember that electrons flow from negative to positive. So electron flow is going to be this way. The magnetic field points north to south. So let's clean this up a little bit. Hopefully that helps. Magnetic field points north to south. So we would easily use our left-hand rule and say magnetic field points this way, electricity points that way, so the wire should bend upwards. So the force, the wire actually will bend or deflect. Wire will deflect upwards. Okay, the last piece is something that I believe it was Ampere came up with. He's the guy that came up with current electricity. He's one of the scientists that studied it a lot. And he did a lot of research on not just one wire, but two. So let's do. Okay, so let's have two wires here. Okay, and this is the first wire. Okay, and we're just going to represent by a cross section where the current itself flows through the wire into the page. And then we're going to have another wire where the current also flows into the page. So the current is flowing in the same direction. So imagine two wires where the current flows into the page. Now, the electricity is flowing into the page. The electrons are flowing into the page, is what I'm trying to say. And so we can use our left-hand rule to draw the magnetic field that will be produced on each one. And since they're both flowing in the same direction, they're both negative charge, the magnetic field should loop around like so. So we might say this is counterclockwise. And the same can be said here. So two wonderful circles. And what we want to do is kind of say, remember, this is about how does flowing electric charge behave in the presence of an external magnetic field? Well, this magnetic field is produced by this wire. So we want to say, how does the magnetic field produced by this wire affect the other wire? And so I've kind of done this in two different colors, black and blue. So let's start with the blue first. This particular magnetic field points upwards, and the wire points into the page. I'm not really talking about that wire, I'm talking about this one. This wire points into the page, so that's like so, downwards. Thumb would point downwards, and the magnetic field points right here upwards. Does that make sense? So this wire directionality is downwards, and this wire is affected by this magnetic field, and it points upwards. So the deflecting force would be to the left. So I'm going to draw that kind of right here. This wire should deflect to the left. And then we can do a similar thing. We can say, okay, this wire here also points into the page. And this wire here points into the page, and it is affected by that magnetic field. So it points to the left. I think I just did that. I just talked about it oddly. Yeah, so this wire here points into the page, and it's affected by this magnetic field, and so it deflects to the left. Yes. Now, this wire points into the page, and it's affected by that magnetic field, which is pointing down. We don't really count these. They're equally distant away and in opposite directions, so they'll cancel. And then this is even further away, and the way fields work is the further away you are, the less you're effective. So really, we say that this is the only part of the magnetic field produced by this wire that affects this wire. So, just in case you were wondering. So this wire points downwards, and then the magnetic field points not upwards, but downwards. So it's kind of hard to draw, but it's kind of hard to do in front of the camera. However, if you do that, you'll find that the deflecting force is to the right. And so what Ampere discovered was that two wires that flow in the same direction will actually produce magnetic fields individually that affect the other wire that cause the wires to attract together. Conversely, you can have two wires where one flows out of the page and the other flows into the page. We'll do that one in blue again. We can say, okay, well, let's kind of rinse and repeat the same idea. So this magnetic field would be exactly the same. So we didn't draw anything different. However, this, because the electricity is flowing in the opposite direction, the magnetic field should also point in the opposite direction. So we draw all of our arrows opposite. So now, instead of counterclockwise, we have counterclockwise and clockwise. And so, what we will find, and you can do the left-hand, right-hand rules yourself, is that this particular wire is pushed away by this magnetic field, and this particular wire here is also pushed away. And so the main kind of thoughts here are that two wires where their electricity flows in the same direction will attract each other, and conversely, two wires where their electricity flows in opposite direction, and there will actually be a repulsive force between them. That is everything that we want to cover today. Talk soon.